Hello everyone, welcome to the session of Design of Machine Elements 1. So I am Purushotham, working as Assistant Professor in Department of Mechanical Engineering, Mahadevan Institute of Technology, Mysore. So in the previous sessions, we finished the module 1, that is Introduction and Design for Static Strength. We are moving on to the module 2, that is Impact Strength and Fatigue Strength. So first we will take up impact strength. In the future sessions we are going to see the fatigue strength. So today's session is about impact load, impact stress, impact energy and impact stress induced due to the axial load. So before moving on to the impact load, so first we need to know the meaning of static load and dynamic load. Static loads and dynamic loads. So static loads are the loads which act or which applies gradually on the working component or machine components. So that means which gives any sufficient time for the deformation. So due to the static strength, the component will fail in three modes. The first one is failure mode due to the elastic deformation, and failure due to the yielding, and failure due to the fracture. So we can see in simple tension test, the specimen which is subjected to the loading condition of tensile load, that is gradually applied. We are going to apply the load gradually like this. So from this, the material which is going to elongate. Then in static load, one of the important parameter is we are not going to change the direction of application of load. That means tensile means throughout the ending process, throughout the testing, we are going to apply the tensile load only. For the few loading conditions, we are going to apply tensile. For the further, we are not going to change the direction of load in static loads. So coming to the dynamic loads, the dynamic loads which vary in magnitude, direction, or both in magnitude and direction, which is called as dynamic loads. So variable loads and impact loads are some of the example for dynamic loads. Variable loads, which is nothing but the fatigue loads. That means the load which repeated cyclically like this. The load which repeated cyclically, if you can see this will be the time, this will be the stress, so this will be the magnitude. So you can see the load which is changing its magnitude from 0 to some point. For example, I will take which is around 50 megapascal. So which is changing its magnitude as well as its direction from positive to which is going on to the negative, that is which is load is applying and releasing. So which is changing the magnitude as well as the direction in variable load. Now coming to the impact load. So when you are going to say impact load, the load must be applied with some initial velocity. So the machines which is undergone for impact loads, we can see the presses, so which is used for the blanking operation as well as the forging machines. So you can see in the forging laboratory, the hammer which is going to hold at a certain height, that means the potential energy which is going to store. So when you are going to hammer on the workpiece art model, that means the potential energy which is going to convert it into kinetic energy, that means so which is going to the load which is gaining some initial velocity. So that is used to deform the required size and shape of the workpiece. So that is called as impact load. That means the load which is having some initial velocity, which is called as impact load. Then coming to impact stress. If a moving object, for example, you can see this will be the moving object which is going to strike the another object, which is going to strike the another body, then this body which is subjected to impact, and this impact which is equal to the kinetic energy of this moving object. So this will be the moving object which is going to strike this another body, then this body which is subjected to impact, which is equal to the kinetic energy of the moving body. Simply we can say the stresses which is induced due to the impact load, which is called as impact stress. Stresses which is induced due to the impact load, which is called as impact stress. So next we are moving on to the impact energy. So when the body which is having a weight of W, that is moving body weight is W, then which is having some initial velocity V, then kinetic energy Ek, as we know that the kinetic energy formula is of mv square, which is given by, I am going to represent the mass in terms of weight, so which is given by W by G into V square So finally which is given by WV square by 2G. This will be the kinetic energy of the moving body. So this will be in the data handbook equation number 2.25a and page number 27. Now, but for the stress calculations, so we need to convert. So the impact energy that is as to express in terms of height of falling object. So for the convenient purpose, we are going to express the impact energy in terms of height of falling object, that is height of fall. For this, h will be the height of fall and v will be the velocity of the moving object. Then height of fall is given by v square by 2g. Height of fall is given by v square by 2g. Now I am going to substitute in this equation. So you can see this kinetic energy now which is given by v square by 2g, that can be replaced by using the term h, that is height of fall. Now this equation which becomes w into h. So this will be equation number which is available in the data handbook, which is 2.25b, page number 27. Then so this will be the equation for kinetic energy of the moving body, but as we know that the impact energy which is equal to the kinetic energy of the moving body, then this one which is equal to impact energy. So that means this equation which is equal to applicable to the impact energy. Next we move on to the impact stress induced due to the axial load. So the impact stress which are induced due to axial load, bending load and torsional loads. So first we are going to see the impact stress which is induced due to axial load. For this purpose I am going to derive an equation. So in that we are going to find out the impact stress which is induced due to the axial load. For this, so I am considering this figure. Here you can see the vertical bar on which a weight of W which is suspended. Now the weight W which is dropped onto the at a height of h on a vertical bar on one end of the vertical bar. So then due to the impact of this weight W, so this bar which is subjected to instantaneous deformation which is given by delta dash. So then which is shown here, that means this will be the initial position of the vertical bar, that is one end of the vertical bar due to the impact of this weight W, so which is extended like this. This will be the deformation, instantaneous deformation due to the impact load. So for the derivation purpose, so we need to aware of this some symbols where, so I am going to use letter or notation A, that is cross sectional area of the vertical bar, then E means Young's modulus of the vertical bar, L will be the length of the vertical bar and delta dash, that is instantaneous deformation due to impact load, and sigma dash, that is the stress induced due to the impact load, then H, that is height of fall, then delta, this will be the static deformation due to the weight W, then W, that is the weight of the moving object, then P. So the force at which impact stress is induced, the force at which the delta dash or impact stress which induced, which is called as P. Now for this purpose, first I will consider the work done by the falling body which is equal to change its potential energy. That means at initial stage the potential energy which is stored as W into H. So at this side the weight is, this will be the potential energy. When this weight W which is impact on one end of the vertical bar, then the potential energy will changes. That means the work done by falling body, so which is equal to change in potential energy, which is given by equation W times of H plus delta dash. Initially which is WH, after impact which resembles W delta dash, that is instantaneous deformation which occurs. Then the energy gained by the system which is equal to potential energy lost by the weight. For example, if you consider this will be the deformation, that is deformation due to impact load, this will be the resisting force which is equal to the applied load P. So when you are going to apply a load, when you are going to apply load, then the resisting force which is going to develop in the body. In the same time, in the meantime, the deformation which is also occurs. So when? So as we know that the resisting force which is equal to the applied force. So if you are taken the area under this curve, that means the body which stores some energy here. So this energy which is called as strain energy. Now the area under this curve, if you can see this will be look like triangle. So area of triangle which is given by half into base into height. Half into base into height. Now this will be given by the energy stored in a body. Base is what? The deformation, static or instantaneous deformation. Then the height is what? The resisting force which is equal to the force which induces the instantaneous deformation. This will be the energy gained by the body. So which is shown here, half into P into delta dash, which is energy gained by the system, which is equal to potential energy lost by the weight, that is change in potential energy. Now in this letter P, the load which is given by sigma dash into A, that is, as we know this, sigma dash which is given by force by area. So then P is given by sigma dash into A. So which is shown here. Next, so the delta dash which is equal to sigma dash into L by E. So which is given by, we know that sigma dash which is equal to E into epsilon dash, where sigma dash which is stress induced due to impact load, epsilon that is strain due to impact load. Then E is given, E equals E into epsilon dash, that is delta dash by L, that is change in length, instantaneous deformation by original length. Then sigma dash into L divided by E, which is given by epsilon dash, that is delta dash. So from this equation we can say delta dash which is equal to sigma dash into L by E. Now I am going to substitute these two terms in the above equation 1, then which is given by half into, in the place of P I am going to replace sigma dash into A, and in the place of delta dash I am going to replace sigma dash into L by E, which is equal to W times H plus, in the place of delta dash sigma dash into L by E. So then if you are simplify this, then sigma dash square plus AL by 2E, which is equal to WH plus WL by E into sigma dash. So finally this equation which reduces into the quadratic equation form, that is AL by 2E by sigma dash square minus WL by E into sigma dash minus WH, which is equal to 0. So the equation which reduces into the quadratic equation form, AL by 2E sigma 1 square minus WL by E sigma dash minus WH into 0. So this one which is in the form of AX square plus BX plus C, which is equal to 0, that is quadratic equation. The roots for these equations are x is given by minus b plus or minus square root of b square minus 4ac divided by 2a. So that is by this equation, so the quadratic equation root is this one. Now this one which is also in the quadratic equation form, from this we can say the value of a which is equal to AL by 2E, then value of B which is equal to minus WL by E, then value of C which is equal to minus WH. So now I am going to substitute these values in this standard equation, then you will get sigma dash. Here x is the root, here what we need, sigma dash which is equal to WL by E plus or minus square root of WL by E whole square, then so this one become plus just because minus WH. So minus of minus become plus 4AC, that is AL by 2E into C is WH. Then divided by 2A, that is 2 into AL by 2E. Here I can cancel 2 ones are 2 twos are, then 2 and 2. So this will be get cancelled. Then WL by E plus or minus. So here I am going to take WL by E whole square as a common factor. In this term I am going to take WL by E whole square as a common factor. Then you will get 1 plus 2H AE by WL. AE by WL. If you are going to solve this, then you will get 1 plus 2H AE by WL. Here in the denominator we will left out with AL by E. Now I am going to take, in the previous equation, I am going to take WL by E, the square root for this term, then this term which comes outside, that is WL by E plus or minus WL by E square root of 1 plus 2H EA by WL divided by AL by E. AL by E. Then in this equation, I am going to take WL by E as common factor, then you will get 1 plus or minus square root of 1 plus 2H EA by WL divided by AL by E. Then we are moving on to next we are going to take, so separate wise, that is sigma dash which is equal to W by A plus or minus W by A into square root of 1 plus 2H EA by WL. For the impact stress, we are going to consider the positive sign. So for this, I am going to ignore this negative sign. So then taking common factor, you will get sigma dash which is equal to W by A into 1 plus, in terms of plus or minus, I am going to use the plus sign. So consider positive sign, then 1 plus square root of 1 plus 2H by EA by WL. So this will be the impact stress equation, so which is available in the data handbook 2.26a in the page number 27. So further we are going to represent this equation in terms of static deformation as well as instantaneous deformation. In the previous step we derived this equation sigma dash which is equal to W by A terms of 1 plus square root of 1 plus 2H EA by WL. So this will be called as 2.26a equation. Now I am going to take this equation as equation number 3. Now for this equation, this will be reduced into sigma dash which is equal to the W by A which can be replaced by sigma. So the sigma which is the stress induced due to the static load. So then 1 plus square root of 1 plus 2H by delta, this term EA by WL, this will be replaced by 1 by delta. So this will be given by, as we know that sigma which is given by E into epsilon, that is strain. So E into epsilon strain is given by deformation, change in deformation by virginal length. Then sigma is given by W by A. So if you solve this equation in terms of delta, we will get WL by EA. But in this equation, we are having EA by WL. So for this I am going to take 1 by delta, that is reciprocal of delta in this equation. That is, this will be relate the impact stress in terms of static deformation as well as the static stress. So this will be available in the data handbook 2.26a page number 27. Next, so for this, the equation number 3, for this equation I am going to multiply both sides by L by E. So if you are going to multiply this, sigma dash into L by E which is equal to W into A into L by E plus into 1 plus square root of 1 plus 2H EA by WL, then sigma dash into L by E, so which is given by delta dash, that is instantaneous deformation due to the impact load, which is equal to then this one WL by AE. So as we shown here, WL by AE which is given by static deformation into 1 plus square root of 1 plus 2H EA by WL. So this will be available in the data handbook in the equation number 2.26p page number 27. If you are observe this equation, these two equations, so here the term 1 plus 1 square root of 1 plus 2H EA by WL or 1 plus square root of 1 plus 2h by delta, these two terms which is called as impact factor. Just because these terms, so as we are observe this will be the impact stress, this will be the static stress, this term which is going to relate the impact stress with the static stress. So here also this will be the deformation due to the impact load, this will be the static load deformation, this term which is going to relate deformation due to the impact stress due to the deformation due to the static load. That's why which is called as impact factor, which converts the effect of height of fall to the equivalent static force. So this will be the derivations which is about impact stress which induces due to the axial load. We derived the impact stress due to the axial load. From that we got the sigma dash, that is the impact stress which is induced due to the impact load, which is equal to W by A. So 1 plus square root of 1 plus 2h EA by WL. So which is in the equations which is in the data handbook 2.26a, page number 27. In terms of our deformation which induced due to the impact load, which is given by delta dash, which is equal to delta times of 1 plus square root of 1 plus 2h EA by WL, which is available in the data handbook 2.26b, page number 27. So in the same way, if you are going to derive the equation for the bending load as well as the torsional load, you can see here the beam which is subjected to a impact load of W, the height of fall is h, then due to the falling or dropping of weight W from the height h, the beam which is subjected to deflection which is called as y dash, that is instantaneous deflection due to the impact load W. So based on this, if you are derive the equation, then impact stress due to bending load which is given by sigma b dash, which is equal to sigma b times of 1 plus square root of 1 plus 2h by y. So where h is height of fall and y which is equal to the deflection which is due to the static load. So then which is also available in the data handbook, equation number 2.26c, page number 27. So in the same way, in terms of deflection, instantaneous deflection due to impact load and deflection due to the static load, both are related by using equation y dash which is equal to y times of 1 plus square root of 1 plus 2h by y, which is available in the data handbook 2.26d, page number 28. Now the impact stress which is due to the torsional load which is given by tau dash, that is impact stress which induces due to the torsional impact load which is equal to tau. This tau, that is the torsional load which is due to the static load. So which is tau times of 1 plus square root of 1 plus 2h by theta. Here theta is the angular deformation due to the static load which is available in the equation data handbook 2.26e. Then in terms of angular deformation due to impact load and angular deformation due to static load, both are related by using this equation theta dash which is equal to theta times of 1 plus square root of 1 plus 2h by r theta. So which is available in the data handbook 2.26 times 2.26f equation, where r is the moment arm of the load W, that is whatever the impact load which is going to applied on the member. So due to that there will be a moment, so that moment which is called as r. Then coming to effect of inertia, that means when two moving bodies, for example I am going to take W will be the moving body which is going to hit or strike another body, so which is having a mass of weight of W dash. Then due to the collision, law of collision of two perfect bodies, then the potential energy WH which is going to reduced into NWH. That means when, if you are seeing this will be the weight W when which is going to fall on the member. So now initially the member or component which is at rest, the weight, the potential energy W into H, the sum part of the energy which reduce due to the overcome this inertia effect of the component. So which is given by equation that reduced potential energy which is given by N which is equal to 1 plus Am divided by 1 plus Bm whole square. So where M is given by W dash then divided by W, and A and B are the coefficients which is available in the table 2.8 page number 34. These A and B coefficients which depends on the cantilever beam or the simply supported beam, that is the load, central load which is going to strike on the simply supported beam, and longitudinal bar. Next we move on to the topic resilience and toughness. So first of all, what do you mean by resilience? Resilience is the ability of the material to absorb the energy within the elastic limit. So that means this resilience which is measured in terms of deformation or strain, that is called as strain energy. For example, I am going to take a stress strain curve for, so this will be strain, this will be stress strain curve for mild steel. Okay, as we know that, so this will be the elastic limit, this will be the upper yield point, this will be the lower yield point, and this one is ultimate stress point, this will be the fracture or failure point. So as we know this, when you are going to apply load, so then the deformation, the body which is going to develop the resisting force which is equal to the applied load, as well as in the meanwhile the deformation which is also occurs. So this deformation which are measured in terms of strain, then this area under this curve, so that is the energy stored in the material due to application of load. So this area under this curve, so which is called as strain energy, So this, so the ability of the material to absorb energy within the elastic limit. Here the important thing is the energy stored within the elastic limit, that is called as resilience. Then the modulus of resilience. So for modulus of resilience means modulus of resilience, that is whatever the energy stored in the material within the elastic limit which is called as strain energy. So the strain energy per unit volume which is called as modulus of resilience, Then moving on to the toughness, so which is also ability of the material to absorb energy and plastic deformation up, so within fracture limit. That means we are going to take the energy up to the fracture, that means the energy absorbed up to this point. So in resilience we are going to measure the energy absorbed up to elastic limit only, but while coming to toughness we are going to measure the energy which is absorbed up to the fracture, then this one which is called as toughness, So based on this resilience and toughness, we are going to solve some problems. For this, the resilience in tension and compression, which is given by equation U equals sigma square V by 2E. So this will be available in the data and book, equation number 2.27b, page number 29. So this will be the resilience in tension or compression. So where sigma square, that will be the stress induced due to the impact load, V will be the volume. So volume which is given by area into length of the specimen, where E equals Young's modulus of the material. Then for modulus of resilience is given by, so I am going to take strain energy per unit volume, that is sigma square V by 2E divided by V, then we get sigma square by 2E. So this will be called as modulus of resilience. Then for the same case, resilience in torsion due to torsion, which is given by, so that US, which is equal to tau E square divided by 4G. So this will be available in the table 2.9, page number 34. So resilience in torsion, which is given by US, which is equal to tau E square by 4G, where G is the modulus of rigidity, that is the material property. So this will be the modulus of resilience in torsion. So based on, by using these two equations, we are going to solve some problems in resilience as well as the toughness.